In the previous video, you learned about a lens's resolving limitation. Now you will explore some additional characteristics of a lens that can be important in your machine vision imaging. In this video, you will cover depth of field, the Scheimpflug condition for good focus, the cosine to the fourth power effect and the light gathering power of a lens, and the optical invariant. So let's get started. Let's turn our attention to another facet of imaging, depth of field. Depth of field is defined as the range of object distance over which the image appears to be in sharp focus. Although there are formulas for calculating depth of field, the definition makes it plain that it is more subjective than objective. We will first start by defining depth of focus. This diagram shows a theoretical lens focusing a point to a point. In any image sensor, the pixels have a certain size. If we map that size onto our diagram, both in front and behind of the focus spot, we can see there is a range of image distances over which the image will appear to be in sharp focus. This range of image distances is the depth of focus. Let's see how this works going out to the scene being imaged. Starting with the focus point, we can draw in our pixel's height. Then we project the pixel to the object plane to see where it would focus, both for near and far conditions. This is the range of focus in object space depth of field. There are a number of equations for calculating approximately the depth of field. Some work better under some conditions and some work better in other conditions. Several formulas are provided in the paper on machine vision optics you can download. The URL is given at the end of this video. Sometimes you cannot place a camera to image the scene perpendicularly. Let's look into what happens when imaging a scene at an angle. We will see that it is still possible to keep the scene in sharp focus even with a very shallow depth of field if we can satisfy the Scheimpflug condition. Here is the common imaging situation. The scene or object plane, the principal plane of the lens, and the imaging plane are all parallel. If the object plane is tilted with respect to the lens, then either the image plane or the lens must also be tilted to retain good focus across the image. The Scheimpflug condition tells us that the three planes, object, principal, and image, must all intersect along a common line to maintain focus across the scene. So far we have treated the lens as if it gathers the same amount of light from the entire scene. On closer examination, we can see that this is not accurate. Here is the imaging condition. The lens is gathering light from the scene through the triangle shown. Actually, the triangle represents a cone having some solid angle. If we examine what happens when the lens collects light away from the center of the image, we see that the triangle becomes narrower. This narrowing of the triangle represents a reduction in the solid angle the lens can use to gather light. The solid angle decreases as the cosine to the second power. In addition to this reduction, under common imaging conditions, the light from the scene into the lens's solid angle also decreases as a cosine to the second power. The result is, for normal lenses, the light gathered by a lens decreases by the cosine of the angle to the fourth power. For long focal length lenses, the shading caused by the cosine to the fourth power is negligible. However, for short focal length lenses, it can become more significant. How many hours have very bright engineers worked to overcome the laws of physics when designing imaging? Too many, I'm sure. To understand the limit, we need to explore the optical invariant. If we look at a simple diagram of imaging with an object of some height and a marginal ray that passes through the edge of the lens, the product of the object height and the tangent of the marginal ray angle defines a constant. If we look at the image side, we also see an identical equation using the image height and the tangent of the marginal ray on the image side. This constant is an invariant. We cannot increase it no matter how many lenses we use or what type of lenses we use. Although called the optical invariant, we can change it, but only in one direction. We can make it smaller by using stops in the optical path. The stop has the effect of reducing the effective size of the marginal ray from the object, so the invariant is changed, but still remains invariant. The optical invariant presents problems when an engineer attempts to cascade lenses to change the characteristic object-to-image distance relationship. Now you know more real-world attributes of imaging, how depth of field limits what remains in focus as the working distance of our lens changes, the Scheimpflug condition that is necessary to keep tilted scenes in focus, the cosine to the fourth effect on a lens's light-gathering power, and the optical invariant that limits what we can achieve with imaging. For more information on light, as well as many other related topics that you will find useful in your work in machine vision, download the paper Optics for Machine Vision Practitioners at the URL shown here.